Hello, this is Professor Doug, and we are moving on to Chapter 6 in Mechanics of Materials. And this chapter deals with bending. So we will begin by looking at a few examples using Excel, and we will develop shear and moment diagrams in Excel, which actually are quite illustrative and can be done rather simply. And then we will look at a problem involving bending forces. So let's begin with an example of shear and moment diagrams. So this example is example 6-3. And you can see it's a very interesting example because we have a simply supported beam. This is the upper figure here, and it's 18 feet in length. It has a roller support on the left end and a hinge on the right end, and an interesting trapezoidal load that grows or increases from 2 kips per foot on the left end up to linearly up to 6 kips per foot on the right end. So the first order of business for this is to determine the support reactions. So in order to determine the support reactions, we need to do some simple mathematics, and we can enter the beam length here. The trapezoidal load begins at 2 and terminates at 6, so I've entered those here. And we're calling W sub O the 2 and W right 6 kips per foot. So we will break that down, as you may have seen in other lectures in this course or in similar courses. If you have a load of this configuration, you want to break it down into a rectangular load sitting beneath a triangular load. And you can see that in the middle illustration. So the rectangular load begins at 2 kips per foot and uniformly is distributed across the 18-foot beam. Okay, so there's the 2 kips per foot and the 18-foot beam. If you multiply 2 kips per foot by 18 feet, you get 36 kips. So we're replacing the distributed rectangular load of 2 kips per foot across 18 feet with a point load of 36 kips. That's in the box. And where do we put it? Well, because it's rectangular and the beam's 18 feet, you put it halfway, so it's at 9 feet. So that'd basically be 18 over 2. Okay, so that's the first part. The triangular load that remains then begins at 0 kips per foot on the left and increases linearly to 4 kips per foot. Where do we get those numbers? Well, if you subtract 2 kips per foot from both sides here, you get 0 and 4, and that then becomes a triangle because we have removed a rectangle uniformly distributed load of 2 kips per foot across the beam. Now we're left with a triangular load increasing from 0 to 4 kips per foot. So it's just subtraction. So that's what you see here. So the distance is still 18 feet for that triangular load. And basically, we converted a trapezoidal load into a rectangle sitting below a triangle. Okay, and then you want to multiply that 4 by 18 and you get 72, but then you want to divide by 2 because it's a triangle, and that gives you another point load of 36 kips, and there you can see them side by side. Well, that's placed at the centroid of the triangle, which is 2/3 of the distance from the left end to the right end. So 2/3 of the distance from where you have no load to maximum load. So that's going to be 2/3 of 18, which is 12. And so there's our geometry. Now, where do these 30 and 42 kip loads come from? Well, in order to calculate them accurately, you need to take the moments about the left end. And the summation of the moments is 0 because the beam's in equilibrium, but we've got 2 point loads of 36 at different locations from the left end distances. So you're just multiplying those loads by their distance. So the distance is the arm and the load is the kip load, and then you get these numbers. Now, why are they negative? Because they both will create clockwise moments around A, and the convention is that clockwise is negative. So if you sum these, you get minus 756. But then you have a reaction support at B that will create a counterclockwise moment around the left end. Okay, when I say A, I mean the left end, and B, the right end. And so if we divide this minus 756 by minus 18 because it's going to create counterclockwise, we get 42. So 42 kips is the load at the right end. And because the sum of the forces in the y direction is 0 and there are no forces in the x direction to deal with, then 36 and 36 down is 72. So you must balance that with 72 kips up. So 72 minus 42 is 30. That's the easiest way to do this. Now, there's another way to do it if you're adept at such a thing. If you have a rectangular load with a 36 kip point load replacing the rectangular distributed load halfway between the left and the right end, that means you'll have 18 left and 18 right pointing up. Okay, that's just park that there. All right. So then you have 36 kips at 2/3 of the distance, excuse me, of 18 feet here with this other load on the right. So I'm only talking about the point loads now. So 36 kips at the center is going to be 18 and 18 at the supports, and that balances to 36. But you have another 36, 2/3. So 2/3 of the 36 would be at the end of the beam that's closer to the load. 2/3 of the 36 is going to be, let's just calculate that real quickly, 36 divided by 3 times 2, that's 24. So you're going to add 24 to that half of the 36. 18 plus 24, you're going to get 42. And then on the other side, 1/3 of this 36 kip load would be supporting on the left. So 1/3 of 36 is 12. So you had 18 plus 12, you get 30. So you could essentially do this that way, which is really kind of doing it in your head. But I would suggest the sums of the moments and take the moments method and make sure you observe the signage, negative or positive, correctly. So that part is done. We now move on to setup for the shear and moment diagrams. This is more complicated. We want to draw the shear and moment diagrams in Excel, or illustrate them. So we're going to cut the beam. This is the final illustration at the bottom here. Cut the beam at some distance x from the left end. We know that there's a 30 kip load up, and what we're going to get is a shear downward V at the cut and a moment, which is counterclockwise, which is assumed positive at the cut as well, due to these loads. So, and supports. So the new rectangular point load then is now just Wx, so that's 2x, and that would be this as shown here, 2x pointing down. And the new triangular point load is 1/2 of W max, and W max was over here as 4, right? And times x over L, that's the distance, x, which is the cut over the length, 18, original, times x. So that's shown here. So if you simplify this, you get, due to the summation of all forces in the y direction being 0, you get 30 kips up minus 2x kips down minus 1/2 times 4 times x squared over 18 kips down minus v equals 0. All right, so that's all these dark black arrows that are pointing up or down vertically only here. Okay, so we can simplify that to come up with a shear equation. It's 30 minus 2x minus 1/9 x squared. So that's a quadratic equation. All right. And we want to find the root of the quadratic. Now that can be done with another Excel function, but we're simply going to do it with what if analysis in this case. And perhaps at another time we'll use the root function for quadratics. And then the moment equation is the integration of the shear function, the integral. So you have to do that a little old-fashioned integration by hand. So if you're familiar with integration, you integrate the shear function, you get the moment function. The moment function would be then 30x minus x squared minus x cubed over 27. Okay, so if you're not familiar with how these were derived, you'll have to review your integration. It's really just power rule integration, and this should be plus constant, but we're going to assume that constant is 0 because our moment diagram starts and begins at 0. So we want to know two things. We set up a column of beam lengths, and we're only going to increase it by 1. So technically, you could just actually type 0 and 1, and then drag this down and populate the rest of the table. Then our shear function is here, and our moment function is here. So these are the functions. You're taking 30 as a constant in both cases. you're subtracting 2 times whatever the x value is, and then from the shear, and then minus 1/9 of whatever the x value squared is, and then you will get that. You can see there's the equation up here in the formula bar, and you're just going to copy that. You only have to type it once, as you know, and then you'll just copy it down like so. And then the moment equation is here, so same thing. You're going to enter the equation directly, and you only need it once. And it should start and end at 0, and then you can just drag it down. Now, you can see I've plotted these, right? And I plotted a shear as x versus v sub x, and a moment as x, hold down the control key, versus m sub x, and that's in red. So there's our shear and moment diagrams. In order to determine the maximum shear and moment, which is the goal here, we want to know where the 0 crossing is of the shear function. That's the root of the quadratic, the real root of the quadratic equation, right? So what you can do is just actually take your table and pull it down a little bit. And I'm going to put some gray in this block right here, and we're going to reformat that so we can calculate this. And we don't know, it looks like the shear function crosses 0 somewhere between 9 and 10 because it goes negative, right? So let's just throw in a dummy value of 9.5. And we didn't get 0 for our shear, so that means that's not the maximum moment, but we're pretty close to the apex of this is a cubic function, right? The apex of that function here is your maximum moment. It's also the same x value or length value as where the 0 crossing is on the shear function. So what we can do is just do what we've done before, is go to data, what if analysis, goal seek, and we can set the shear function value equal to 0 by changing the x value, which is the length, and it'll calculate it for you. Okay, so there's your maximum shear is 9.735, and that is the distance x, and I'm sorry, the maximum moment is calculated as the 0 of the shear function. So where does the shear function cross 0 kips? It crosses it at 9.735 feet into the beam. Okay, and then that means that our maximum moment, the apex of that cubic function, is also at that same distance at 9.7345 feet in length, and that would be 163.11 roughly. And moment, as you know, is in foot kips, and shear is in kips. And so the problem here is solved. And now we're going to move on to a bending problem from this chapter. So it says a box beam here is constructed from 4 pieces of wood. So this is a composite glued together. Okay, glued together. If the moment applied here, and you can see the moment applied is a blue clockwise oriented moment, determine the resultant force the moment exerts on the top and bottom boards of the beam. All right, well, this is an interesting problem because we have to first type in our given parameters, and our outer height is going to be 10, our outer base is 8, our inner height is 8, and our inner base is 6. You can just see that from the dimensions here, and make sure you're adding, the 1-inch thickness of the outer pieces of wood. So that's by inspection. No real calculations needed for the height and base of inner and outer. Why do we need both inner and outer? So we can calculate the outer area moment of inertia, which is 1/12 bh cubed, and the inner area moment of inertia. Then we just subtract inner from outer and get our total area moment of inertia for this composite beam. So that's just simply 1/12 base times the height cubed, and you have to use the respective outer and inner base and height values to get these calculations. So they're simple calculations. The units are inches to the 4th. So now that we have that, we need to know what's our neutral axis to the top fiber. So the neutral axis is shown as a horizontal line running from right to left or left to right, right through the center of this. So if you look at that line, you go up 4 and then 1 more to the top fiber, the outer fiber. So let's see the distance from the neutral axis to the top fiber is 5 inches, right? It's just the outer height over 2. So you can just divide this by 2. So the applied moment is given as 10 kips per foot, foot kips. Let's convert that to kip inches by multiplying by 12, because everything needs to be in that unit since we're in inches now, kips and inches. So the bending stress is just simply sigma bending is MC over I. So M is 120 kip inches, C is 5 inches, so 120 times 5. And you can take a look at that as, a simple calculation. Times 5 is 125 times 5 is 600, right? Kip inch squared. And then you're dividing it by inches to the fourth by this 410 value, right? So let's check that. Yep, you're dividing it by the 410, and you get 1.461 KSI, and that occurs at the outer fiber, the bottom of the lower board. All right. Then if we look at sigma at the 4-inch mark, which is the inner height divided by 2, we use the same calculation, but we get a different value, and this time C is going to be 4 instead of 5. Okay. So here are our two values calculated, and that occurs at the top of the lower board. So we have bottom of the lower board, top of the lower board, and that's shown in this illustration here on the left. And you can see you've got a trapezoid, but it's a three-dimensional trapezoid, and its base 1 and base 2 are either 1.1688 and 1.4610 KSI respectively, or you could reverse those and call them B2 and B1. It doesn't matter. The height is 1 and the depth is 8. So it's a three-dimensional trapezoid, and so we want to actually calculate the resultant force F as the area of this three-dimensional trapezoid. So it's just 1/2 base 1 plus base 2 times the height, 1 times the width, B19, which is 8, which is the outer base here. And then you've got 10.52 kips for a solution.